All right. So today we're going to talk about indeterminate forms and this thing called L'Hopital's rule. Um, and basically, uh, if you remember back to um, when we first started doing limits, and when we would get something like 0/0, and then we'd have to do some algebra and try to figure out what that limit is. Um, this that 0/0 is what we call an indeterminate form, and L'Hopital's rule is a way to deal with that. So um, we'll just take a look. So one indeterminate form is if you have 0/0. For instance, if we took the limit as x approaches 0 of sine x over x, sine of x at 0 is 0, x at 0 is 0. So, and there's no way to use algebra to eliminate the 0. So that's why we have this thing that we call L'Hopital's rule. So 0/0 is one of our indeterminate forms. The other one is infinity over infinity. It could be negative infinity over negative infinity as well. Um, so if we had the ln of x and x minus 1 as x approaches infinity, um, it's not necessarily going to be 1 as an answer. It could be, but it doesn't have to be. And basically, what determines the value is which function, either the numerator or the denominator, is the stronger function. And so I call it the winner um, in this struggle. The stronger function wins, um, but that's going to determine what our limit is. All right, so here's L'Hopital's rule. Suppose f and g are differentiable. We can take their derivatives. And g prime is not 0 at this value a that we're approaching. Um, then suppose that the limit as x approaches a of f of x over g of x is indeterminate. What we can do is from that limit, take the derivative of the numerator and divide by the derivative of the denominator and take that limit. And if that limit exists, that is the limit of the original function. If it does not exist, or if it gives us another indeterminate form, then we have to move on from there. So just a couple of things with L'Hopital's rule. It's not the quotient rule. So we're not taking the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. No, it's just what you wished the quotient rule would have been. Just take the derivative of the numerator, take the derivative of the denominator, and evaluate it. Excuse me. A couple other things. If we have the limit as x approaches a, f of x over g of x, and we get something like 0 over infinity. That is not an indeterminate form. That would be 0. And if we had the limit as x approaches a of f of x over g of x, and we got infinity over 0, again, not indeterminate, that actually goes to infinity. All right. So one of the first ones we looked at kind of in our examples was what happens if we take the limit as x approaches 0 for sine x over x. And the first thing I would always do is just check what happens when I plug 0 in. And I know we already said that's going to be 0 over 0. So then what I do, I don't use an equal sign. I use a little arrow. And I always put an L. I think the book uses an H. But I use L for La Hopital. They use H for Hopital, I guess. So we're going to take the limit as x approaches 0, and now take the derivatives. And so the derivative of sine x is cosine x, and the derivative of x is 1. And now I can plug in and see if I get a value. Cosine x at 0 is 1. 1 as x approaches 0 is 1. So the limit of sine x divided by x approaches 1. So in this case, we have 0 over 0 at 0, but as we come in from either side, we actually get a value of 1. Okay. Now, a couple of things. This is the limit, so it's not the function value itself. This function is undefined at 0, but the limit exists, and that's what we're finding. Limit as x approaches infinity, ln of x over x minus 1. Again, if I look at what happens as x gets larger and larger, ln of x gets larger and larger. X minus 1 gets larger and larger. So I'm going to use L'Hopital. And what is the derivative of ln of x?
Isn't it 1 over x?
It is. And the derivative of x minus 1, I'll help you with that one. That's a tough one, I know, is 1. If I plug in infinity now, 1 over x as x approaches infinity, that goes to 0. and the denominator is just 1. 0 over 1, that's okay. It's not an indeterminate form. 0 over any constant is just going to be 0. So the first part of your assignment is going to be on 296, 297. Problem 1, and then 5 through 24, skipping 15 and 22. And those will simply be evaluating a limit, and if it's indeterminate, then using L'Hopital's rule. A couple of things that can happen, we didn't have an example like it in the notes, but I should put one in there. But what can happen sometimes is we can have a limit and we get 0 over 0, and so we use L'Hopital's rule. And we still get something that's indeterminate. If that happens, then you just use L'Hopital's rule again. You take another derivative in the numerator, you take another derivative in the denominator. And you can use L'Hopital's rule multiple times as long as you have an indeterminate form that you are using that with. It's not, it's not one of those, well, if it doesn't work the first time, then you're done. If it doesn't work the first time, then you try a second time and a third time, and until either you don't have an indeterminate form or you have your value for your limit. All right. Second part. So there are products that can be indeterminate. So if we have the product of f and g, and the limit for f is 0 and the limit for g goes to infinity, we have what we call an indeterminate product. In this case, 0 times infinity isn't necessarily going to be 0. Now, this isn't in our good indeterminate forms of 0 over 0 or infinity over infinity. So we're going to rewrite it so that it is in one of those forms. And that can be done by taking either f, and instead of multiplying by g, if you divide by 1 over g, which is an equivalent expression, and then you'd have 0 over 0, and then you can use L'Hopital's rule. Or take g and divide by 1 over f. That is now infinity over infinity. You can use L'Hopital's rule and hopefully evaluate the limit. So going from this indeterminate product, we want to write that as an indeterminate quotient, because that's the only form that L'Hopital's rule works for. It has to be a quotient. So we might have something that looks like this. The limit as x approaches 0 from the right of x times ln of x. As x approaches 0 from the right, x goes to 0. The ln of x goes to negative infinity. So this is an indeterminate product. So now I'm going to rewrite the product as a quotient. And so the question always becomes, which should I put in the denominator? And in my mind, it's easier to move the x to the denominator.
Hey, should we be able to see your screen right now, Mr. Gingrich?
Is it not showing? I'm sorry.
Yeah, it just shows the
The homework.
problem.
Is it the homework? Okay. I thought when I just,
Good.
okay. Let me go back one for the definition. Thank you for letting me know that. All right.
Can you go back for one more second?
Oh, for one more second, sure. Oh,
There we go.
all right. All right. So again, I'm trying to determine which of those to move. I always just look at what function is easiest to move. You know, putting 1 over ln of x in the denominator probably isn't the easiest thing to do. Things that are easy to move would be anything with an exponent. So if I think about this as x to the first, I can move it into the denominator and call it x to the negative first. So that would, you know, x to a power, e to the x, you know, any exponential would be easy to move. Trig functions are relatively easy because they all have a reciprocal piece to it. You know, sine, if I go 1 over sine, that's cosecant. If I have tangent, 1 over tangent is cotangent, and so on. So it's just finding a form or finding a function that's easiest to rewrite. And if I then use L'Hopital's rule, I think Tate had said that ln of x, its derivative is 1 over x. The derivative of x to the negative first is the opposite of x to the negative second. I am going to rewrite this. So we get the limit, oops. Now it's an equal sign because I'm not using the L'Hopital again, as far as I know. One over x. And now I can move the negative x to the negative second back up to the numerator and just change the sign of the exponent. And one of my x's here cancels with one of my x's there. So I get the opposite of x. And as x approaches 0, that goes to 0. So in this case, 0 times negative infinity does equal or approaches a value of 0.
So when you rewrote that, Mr. Gingrich,
Yep.
how did you get 1 over x over negative x to the negative
Okay.
2?
Yep. So I took the derivative, right? The derivative of ln of x is 1 over x. And the derivative of
Mhm.
x to the negative first, we bring the exponent down. So that's where the negative comes from. And take x to 1 less power. So if I take -1 minus 1, that's where the negative.
-1.
Okay.
Yep. All right. Thanks.
Not a problem. Another indeterminate form could be a difference. Infinity minus infinity. Excuse me. If you get that indeterminate difference, then we're going to try to write it as a single fraction. So we might have to find common denominators. We might have to rationalize the denominator by multiplying by the conjugate. We might have to factor out a common factor. All sorts of things that can happen to help us to get it written in either infinity over infinity or 0 over 0. So in this case, if we take a look at the limit, as x approaches pi over 2 from the left of secant x minus tangent x, well, secant is 1 over cosine. Cosine at pi over 2 is 0. The reason we need it coming from the left is cosine is positive to the left of pi over 2. So this gives us a positive infinity. If we went from the right, from values greater than pi over 2, it would actually be a negative infinity. In this case, it really doesn't matter, but that's why, that's the reason that we're specifying coming from the left. Tangent at pi over 2, well, tangent is sine over cosine. Sine at pi over 2 is 1. Cosine at pi over 2 is 0. Both are positive to the left of pi over 2, so it's a positive infinity. So now we want to try to write this as a quotient. And so using our trig identities, I already have common denominators, which is nice. So I can write this as 1 minus sine of x over cosine of x. Now, if I plug in pi over 2, I get 1 minus 1, which is 0. Cosine of pi over 2 is 0. Now I have that quotient, so I can use L'Hopital's rule. So taking the derivative of the numerator, derivative of 1 is 0. Derivative of minus sine of x is minus cosine x. The negative just stays with. The derivative of cosine is negative sine. And so the negatives do cancel, which is kind of nice. At pi over 2, cosine is 0. Sine is 1. Again, I think the temptation here is to try to do L'Hopital's again, but this is not an indeterminate form. It's just the value of 0. The most, I don't even want to say difficult, but the one that takes the most work are these things called indeterminate powers. So if you have 0 to the 0 power, one of the things that we learn in algebra pretty early on is anything to the 0 power is 1 except for 0. So we're going to take a look at what possible values that could have, or what values it would approach. Infinity to the 0 power is an indeterminate power. And kind of the odd one, I think, is this 1 to the infinite power. Because, again, we're always told, well, 1 to any power is just 1. Well, 1 to any real number power would be 1. But remember, infinity is not actually a number. It just represents we're getting larger and larger. So to do this, what we'll end up doing is taking the ln, writing an equation and taking the ln of both sides, and then trying to write the right-hand side as an indeterminate form. I know I can just tell by looking at your faces that you're excited to do this. So we'll take a look here in just a second. All right, so calculate the limit as x approaches 0 from the right of 1 plus sine 4x to the power of cotangent x. If I plug 0 in, sine at 4 times 0, which is the same as sine at 0, is 0 plus 1. Cotangent is cosine over sine. So cotangent at 0 would be 1 over 0, or infinity. So that is one of our indeterminate forms. It's an indeterminate power. So take the ln of both sides. And why does that help me? Well, what I can do is use my laws of logarithms, which says I can bring that cotangent from the exponent and write it out front. And if I look now, this would be infinity times the ln of 1, and the ln of 1 is 0. So now it's rewritten from that indeterminate power to an indeterminate product, and then I can rewrite it as a quotient. Again, I think it's easiest to leave the ln in the numerator. And if I move the cotangent to the denominator, well, cotangent is the same as 1 over tangent. Now I have 0 over 0. And I do a happy dance because I can use L'Hopital's rule when I have 0 over 0. The derivative of the numerator is, let's see, 1 plus sine 4x would go in the denominator of a fraction. Its derivative would go in the numerator. For cosine x. I'm going to move that just a little bit. The derivative of tangent is secant squared. If I try to simplify this, cosine at 0 is 1. So I have 1 times 4. Sine at 4 times 0 is 0, plus 1 is 1. Secant squared, well, secant is 1 over cosine. Cosine at 0 is 1, so secant squared at 0 is 1. So I have the ln of y is equal to 4. But I don't want to know what the ln of y is. I want to know what y is. So to undo the ln, I take e of both sides. Whoo! So the indeterminate powers, by far the most work, but the most fun too, I think. You can agree to disagree, I guess. Oops, that's what I wanted to do. So the second assignment, or the second part of your assignment, on page 297, 27 to 34, 39 to 41.